Hello everyone, this is Brianne Pernick. Welcome to Chapter 9, Lesson 3 for Robert Morris University Math 0900. This is our last lesson for week 2. This was a pretty busy week for us, and in this lesson we are going to learn how to add and subtract radical expressions with like radicals, and we're going to add and subtract radical expressions that must first be simplified. So the terms that you must know are like terms and like radicals. So I do want to refresh your memory real quick on what a like term is in algebra. A like term is considered to be any term that contains the same variables and the same exponents. That means that those terms, when looking only at the variable and exponent portions, are like mirror images of each other. We're not worried about their coefficients at this point. We're just worried about their variables and the exponents that belong to those variables. As long as they are identical, that is what makes them a like term. For example, 2a and 3a. Those are like terms because a and a are the same. If I have 5b squared and 9b squared, those are like terms because the b squareds are the same. If I have 6xy squared and 7xy squared, those are like terms because the variables and exponents are identical in those terms. However, if I have 11x squared y and 9xy squared, these are not like terms because the exponents that go with the corresponding variables are not the same. They are not mirror images of each other. So that is what I am referring to when I am talking about like terms. I did want to review that with you very quickly just in case you were unfamiliar with what that term is, because that is something that I need you to know. Okay, so when you are simplifying algebraic expressions, we can combine like terms. So if we were to add 2a and 3a, they could be combined to make 5a. That's like taking all of your a's and putting them in one bucket. Okay, think of your a's like apples. If you have 2 apples sitting on one side of your table and 5 apples sitting on your other side, you can combine them and put them together to make the 5. Okay. If you have your b squared sitting on one side of your table and the 9b squared sitting on the other, you can combine the 5 and the 9 to make 14b squareds all together. That's what's happening when we are combining like terms. Okay? Now, we can also combine like radicals using this exact same concept. Like radicals are considered to be like radicals when the radicand is identical. When the numbers and variables and exponents underneath that radical sign are identical, you can combine using the mathematical operations of addition and subtraction those radicals. So let's take a look at example A. I have 5 root 2 minus 8 root 2. Because my radicand is 2 for both of those terms, I'm allowed to combine those. So what we're going to look at is pretty much we're just going to ignore that radical and look at 5 minus 8 and do that math. When we do 5 minus 8, we get negative 3. So this simplifies to negative 3 root 2. For letter B, glance across that expression. Are the radicals the same? We have a radicand of A, and A. So we're just going to take a look at what operations we're being asked to do. We have 7 plus 3, which makes 10 root a, minus 5 root a, and that's going to give us a final answer of 5 root a. So you're just looking at your coefficients for that radical and taking care of the mathematical operations of addition and subtraction. Please complete examples A and B. Pause the recording. As soon as you're finished, hit play so that we can check your answers together. Okay, at this point, you guys should have been able to complete A and B. Let's check what you've done. You should have seen that in letter A, you do have like radicals since both of your radicands are 11, and you're simply being asked to add them together. So 7 plus 4 makes 11 root 11. In example B, we do have like radicals there. Our radicand is t the whole way across. So we are simply going to do the mathematical operations that we are being asked to do. So we're going to do 4 minus 7 plus 6 minus 2. Now I may have rearranged my terms as I was doing this to make my math a little bit easier. Remember that we are permitted to rearrange terms using that commutative property. So 4 plus 6 does make 10 root t, and then negative 7 and negative 2 makes negative 9 root t, and then 10 minus 9 makes 1 square root t, which is just square root t as your final answer there. Now, I do want to caution you that not all of the terms in an expression will have like radicals. So you have to be very careful as you are going through your problem. Okay? When you're being asked to combine, it's a good idea for you to rearrange those terms to put your like radicals beside each other. Okay, so I would rearrange this to say, well, what are my like radicals? I have 5 root 2a plus 3 root 2a. The other ones are not like radicals, and you are not going to be able to combine them. So now let's take care of the ones that are like radicals. We have 5 plus 3 is 8 root 2a. The other ones are just going to come on down. In math, anything that is just a numerical term is called a constant, and it should always be written last, and variable terms should always be written first. So please make sure that you follow that model as you are taking care of problems. I would like at this moment for you to go ahead and take care of student practice 2 right here. Pause the recording, do the problem, and then we will come back together. Okay, at this point you should have had an opportunity to go through here and combine your radicals. So the first thing that you should have done here is combine your like terms. So another good rule of thumb here is that when you have a radical or an algebraic expression, let me say it this way, your variables should always be listed in alphabetical order. So we would want the term with an x to come first. And then from there, if it has an xy, for example, it would be written second. But this is all stuff that you guys are going to learn as we go. So if yours aren't in the exact same order that I am writing them, that's okay. Okay, it's not wrong. It's just not good algebra. So it's okay. Don't worry. Okay, so now we're going to bring on down the 3 root x because we don't have any other x terms, and now we're simply going to combine. When your signs are different, you subtract and keep the one with the bigger absolute value, so 7 minus 2 makes positive 5 root xy, and we would finish that off with our minus 5 root y. Our next objective here is for us to be able to add and subtract radical expressions that must first be simplified. As you're looking at these, you are going to think to yourself, well, I don't have any like radicals. And you might move on, but you're going to get that problem wrong because you could have simplified these radicals by taking care of a perfect square, factoring out a perfect square, and then you would have like radicals. So you always need to try to simplify your radicals. So we have 2 square root 3 plus 12 can be broken down into 4 times 3 because 12 contains a factor that is a perfect square. So we have to continue to factor that down and evaluate that perfect square. It's unacceptable to leave it if it contains a factor that's a perfect square. So we have 2 square root 3 plus 2 square root 3. Now that we have like radicals, we can combine that and we will have 4 square root 3. Moving on to example B. You, as I mentioned, have to look at the factors for each of those individual radicals to see if they contain a perfect square. You can never leave a number in radical form if there is a perfect square that can be factored out of it. So for 12, we know that we can break that into 4 times 3 minus 27. 27 can be broken into 9 times 3, and 50 can be broken into 25 times 2. So it just so happens that each one of these problems, or those radicals I should say, could have been broken down into a factor that is a perfect square. So now we need to work on evaluating these. So the square root of 4 is 2, so that leaves us with 2 root 3 minus the square root of 9 is 3, so that leaves us with 3 root 3, and the square root of 25 is 5, so that leaves us with 5 square root 2. At this point, we can evaluate our radicals because we have, or I should say we can combine our radicals because we have 2 terms that are like radicals. So 2 minus 3 makes negative 1 root 3 plus 5 square root 2. Now, we don't ever want to write it as negative 1 root 3 because negative 1 root 3 is the same as negative root 3. So what we're going to do is we're actually going to put the 5 root 2 first and then just write minus root 3. If all you had left was just a root 3, you would have just written negative square root 3 and called it a day. You don't need to put the negative 1 there. I just simply wrote it there to show you that whenever you do 2 minus 3, you do get a negative 1. Okay? The preference is that you guys never put a negative 1 there. You just simply put a negative. I just wanted to show it there in case some of you struggle with that concept, okay? I know that there are some that do, and I wanted to show it to you. Okay, at this time I would like you to take a moment and do the student practice A and B. Please pause the recording, complete A and B, and as soon as you're ready, let's come back together and complete them together. Okay, at this point everybody should have had the opportunity to complete A and B. Let's go ahead and work through the simplification of these. Now square root 50 can be broken into 25 times 2. The square root of 18 can be broken into 9 times 2. And the square root of 98 can be broken into 49 times 2. And as we're going through here, let's start to factor out those perfect squares. When we do the evaluating of the square root there, we are going to have 5 root 2 minus 3 root 2 plus 7 root 2. 5 minus 3 is 2. 2 plus 7 gives us 9 square root 2 as a final answer. Moving on to example B. You should have broken 12 into 4 times 3. 18 becomes 9 times 3. Minus 50 becomes 25 times 2. Plus 27 becomes 9 times 3. And I'm going to back up 1 minute because 18 is 9 times 2. I apologize. Okay, now we're ready to evaluate those square roots. So we have 2 root 3 plus 3 root 2 minus 5 root 2 plus 3 root 3. Anything that has a like radicand can be combined. So let's look at the radicands of 3 first. We have 2 plus 3 makes 5 root 3. I'm going to cross them out so that I know that I've used them. And then I have 3 minus 5, which gives me negative 2 root 2 as my final answer. Our next set of examples is going to require us to start incorporating some variables in with our numerical examples. So we're going to follow exactly the same steps that we have just done. Okay? So we're going to break our numbers down and look for those perfect squares. Now 2a cannot be broken down any further, but 8 can. It can break into 4 times 2a. And how about 27? We know that that can break down into 9 times 3a. Notice that I was keeping the perfect square as a factor by itself and then keeping the other factor with the variable. As we continue on here, I'm leaving the 2a alone. I'm going to now evaluate the square root, so I'm left with 2 root 2a plus 3 root 3a. We can now look for anything that has a like radical. And remember that in front of a radical that does not have a coefficient, there is an understood 1. So you can combine those. So we have 1 plus 2 makes 3 root 2a plus 3 root 3a. And that will be our final answer for that problem. So at this point, I would like you guys to go ahead and do student practice number 4. Pause our recording, and whenever you're ready, you can come back and we'll check our work together. Okay, at this point, everybody should have had an opportunity to complete this problem, and you should now be ready to check your work with me. So let's start with the first radical here. We are going to break this into 3 times, well, actually, let's just leave it as a 9, because that is a perfect square, so we can evaluate that. So we're going to leave it as 9x. Okay. Then we're going to have the 8. That can be broken into 4 times 2x minus square root 4x. I'm leaving that as a 4 because it is a perfect square, plus the square root of 50x will break into 25 times 2x. We are now ready to start evaluating our square roots, so we can break this into 3 root x plus 2 times root 2x minus 2 root x plus 5 times root 2x. And now we can begin to add together anything that has a like radical. First, let's start with our x's. We have 3 minus 2. That gives us 1 root x, so I'm just going to write x. Cross those out so that I know I've used them. And then I'm going to look at my 2 x's. 2 plus 5 gives me 7 root 2x. Now, our next example is one in which our original radical has a numerical coefficient. All of the examples that we have looked at before had a coefficient of 1 and understood 1. If you look at each of the radicals in example 5, they all have a unique coefficient. And we have to be very careful about the simplification of these problems because it will require special multiplication as we simplify out that perfect square. Okay, so let's take a look at how this is done. Okay, for the first radical, we know that 20 can be simplified because we can break that into 4 times 5. Then we have 4 times 45, which we can break into 9 times 5. And then we have minus 2 times 80, which we can break into 9 times 10. Okay. All right. Now, as we're moving through here, I still feel like 80 can be broken down more. And it can. I knew that didn't look right to me. Let's change this here. 80 can be broken into 16 times 5. That problem just didn't quite look like it was going to work out right to me. And sometimes that happens to you as you're going through those problems where something looks like there should be a pattern and it's not following a pattern. So you can use that as an indication to you that maybe something's just not quite right. So what I did there was I divided 80 by 5 because every single one of my other radicals all had a 5. And when I divided it by 5, I saw that there was a factor of 16 that went into it, which is a perfect square. So that's how I knew that my problem was not quite right. Okay, so moving on, we're going to continue on here. We're going to now evaluate these perfect squares, but this is where our step is different. Now, as we're going through here, we know that we have to evaluate the square root of 4, which is 2. But when you bump that square root of 2 out, it has to get multiplied to the coefficient. So I'm actually going to show that step here, and eventually you will learn to do this in your head, but I want to show it to you in writing. In the next step, when you evaluate the square root of 9, it's going to get multiplied to the coefficient of 4. And then we have minus 2, and we're going to multiply that by the square root of 16, which is 4 times root 5. So now we need to simplify all of that work that we just did. So we're going to have 6 square root 5 plus 12 square root 5 minus 8 square root 5. Please do not forget that if you have a coefficient, you must multiply by whatever value you are taking out of your radical. And now at this point, since we have like radicals, we can now combine and simplify. So 6 plus 12 makes 18. 18 minus 8 makes 10 square root 5. And that is our final answer for example 5. At this point, I would like for you to try student practice 5. please pause the recording, try this one on your own, and as soon as you're ready, we'll come back together and we'll check our work. Okay, at this point, everybody should have had an opportunity to try this example, and you should be ready to check your work with me. So for the square root of 27, we are going to break this into 9 times 3. Then we have minus 4 square root 3 plus 2 times 25 times 3 to break up the 75. We're going to evaluate the square roots, so we have 3 square root 3. There's nothing to do for our middle term, so we're just going to bring it down. And then as we evaluate the square root for 25, we have to remember to multiply it by that coefficient of 2. So we're going to have 2 times 5 square root 3. We have to take care of that multiplication, so I'm going to rewrite all of this stuff so that I don't forget about it. 2 times 5 makes 10 square root 3. And I can now evaluate all of this by combining my like radicals. So I am going to first add, so I have 3 plus 10 makes 13. 13 minus 4 makes 9 square root 3. And there's my final answer there. We have one more set of examples to show for this lesson, and it is just a big combination of everything that we have done so far. So let's make sure that we can do it. So starting with this first example, we have 3a root 8a plus 2 times 50a cubed. It's a little bit of everything, guys. So we're going to bring down our 3a. We need to break our 8 into 4 times 2a. For the next term, I'm going to bring down the 2. My 50 needs to break into 25 times 2. And my a needs to break into an a squared times a. If you remember that from lesson 2, we take an odd power and break it into a 1 and then subtract the 1 so that we can get the other power there. And now we're ready to evaluate our perfect squares throughout here. So we have 4, the square root of 4 is 2, so we're going to do 3a times 2 square root 2a plus. Now the square root of 25 is 5, so we're going to have 2 times 5. I did that. 2 is not a perfect square, so it's going to stay under my radical. A squared is a perfect square, so I can divide 2 by 2 and get a. So that's going to get multiplied on the outside as well. So what are we left with on the inside of that radical? 2a. If you prefer to break each of those into the individual radicals, go ahead. If you can leave them underneath one radical and simplify the perfect squares out in one step, go ahead. It's up to you. Now we can start to multiply those coefficients back together to simplify. We have 6a root 2a plus 10a root 2a. And adding for our last step, we have 16a root 2a. And there's our final answer. This last example for today, I would like you to go ahead and do on your own. Pause the recording. As soon as you're ready, please play it and we will review the answer together. Okay, at this point, everybody should have had an opportunity to do this one on their own. So we're going to go ahead and review. We should have 2a times 4 times 3a plus 3 times 9 times 3 times a squared times a, all underneath that radical. Now we're going to evaluate out those square roots. So we're going to have 2a times 2, and that leaves us with 3a underneath the radical. Moving on to the next term, I'm going to evaluate my square root of 9, so that's going to leave me with 3 times 3, and look for any other perfect squares underneath that radical, and I have a squared. The square root of a squared is a, so that's going to get multiplied to my coefficients as well. What do I have left under my radical? Just 3a. We can now start to multiply our coefficients. So 2a times 2 is 4a. Root 3a plus 9a root 3a. Add as your final step since we have like radicals, and we should have 13a root 3a. That is the last example that I had for you guys, so you are now prepared at this point to do the homework problems for this section as well as this whole week if you have not yet started. So please, please, please contact me if you have any questions at all. I will be here to help you. Just let me know and we will set something up. Thank you and have a great day.